Welcome back. This is the second lesson and the final one that you're going to be looking at over spring break. And this one is, again, we're going to be attacking one of the last derivative rules that we're going to need to find. We'll actually deal with the logarithms and natural logs and all that stuff when we come back in Chapter 5. But for this topic, even though it's in Chapter 5 at the very end, you actually have all the tools right now to be able to calculate the derivatives of inverse trig functions using the method that I'm going to outline for you and advocate using and demonstrate every single time. So the beauty of this method is that it revolves around only tools that you already have. So in particular, it's going to involve tools about trigonometry and implicit differentiation. Those two skills will come up over and over again in here, and they're both things that you tend to do pretty well on. So what I'm going to do is I'm going to start by giving you kind of the refresher of what you need for the basics from pre-cal involving trig, and then we'll go forward. I'll do some derivations for the first couple of them. We'll talk about the rules themselves, and then I'll show you this method that works really well. This should be a little bit longer than the e to the x video because it's not as intuitive, or it's not as simple as just saying, well, the derivative is the function of itself, and then you're done. There's a little bit more work involved. So to start out with, instead of giving you a handout with 10 of these to do, I'm just going to go through and demonstrate the method to evaluate an expression like this one, because we're going to be running into expressions like this as we go through. They'll be a lot simpler than this one, but the idea behind it is really important. So we want you to evaluate the tangent of the arc sine of x over 4. And if you're one of those people that's kind of trig phobic, you might look at this and just get the heebie-jeebies as you're thinking about how to evaluate something that has so much trig and so much going on really in it. The beauty of this whole thing, though, is that it's actually not difficult to evaluate. If you just think about what this all means. So this thing in here, this arc sine thing, is really just saying that we want to find the tangent of the angle whose sine is x over 4. So we're talking about a specific angle and a specific triangle. So what I advocate doing for these guys is to start by just making this concrete. Instead of talking about the angle whose sine is x over 4, why not just go through and actually, I don't know, let's make that triangle. So there's a triangle. It's a right triangle, because of course it's more interesting and easier to talk about when it's a right triangle. We are going to talk about now the angle. So let's call it an angle theta. I like talking about thetas. That's a terrible theta. There's theta. The angle whose sine is x over 4. So think about it for a second. So covering up that tangent, I can't do it with my hand. See, I'm trying to do it right now, but you can't see it. We are now talking about the angle whose sine is x over 4, opposite over hypotenuse. Well, the angle whose sine is x over 4 is just theta. So really, we're trying to find the tangent of theta. So now in order to do this, in order to calculate out what the tangent of theta is, we do have to do a little bit more work. In particular, we need to know what this side is right down here. Like, what's that base equal to? The way we're going to do that is just with Pythagorean Theorem. Something very easy to do. We've got leg squared. Of course, it's a variable, but who cares? Plus other leg squared. I'm going to go ahead and leave that as a question mark for the moment. So we'll call it question mark squared is equal to hypotenuse squared. And now we've got to figure out what is that missing side. What is that question mark? Well, not hard. We're just going to solve for the question mark. So I'm going to subtract x squared from both sides. So that question mark squared equals 16 minus x squared. And now I'm going to square root everything. And of course I'm going to get that the question mark is equal to the square root of 16 minus x squared. What does that give us? Well, it tells us that right down here, this side is also known as 16 minus x squared. So there we go. Now we've got a full triangle. So what's left? Well, let's just actually figure out what is the tangent of the angle whose sine is x over 4. In other words, what is, this is so much fun to do, I'm going to copy it down and actually bring it down here. We just want to know what is the tangent of theta. Because if we know what the tangent of theta is, we know what the tangent is of the angle whose sine is x over 4. So to wrap this guy up, we just want to know what, shoot, it'd be a really thick pen to write with. We want to know what is the tangent of theta. Well, the tangent of theta, according to our picture, is just going to be the opposite over adjacent, which is also known as x over the square root of 16 minus x squared. So this whole expression here, tangent of the arc sine of x over 4, is all equal to, if you can believe it, x over the square root of 16 minus x squared. So again, we've got an answer. It seems kind of complicated. It seems really abstract. But in reality, we're just turning it into a simple triangle, and we're running from there. So triangle, label the sides, find the missing one with Pythagorean Theorem, and then evaluate the tangent of the angle we're looking at. Again, what's the name of this? Well, this is really just working with inverse trigonometry, because of course arcsine just means the inverse of sine, which is the angle whose sine is whatever happens to be the argument. So again, this is an old skill. Going through it quickly, I'm not giving you all the theoretical underpinnings of it, because again, you should know this from pre-cal. You should be able to evaluate this now that you've seen an example that you thought about a little bit. Okay, so from here, what are we going to do? We're going to go in and we're going to actually start talking about inverse sine, and then start using it to calculate the derivative and derive out an expression for the derivative. So my notes aren't completely ready, so I'm going to go ahead and pause for a second, and I'll do that now. Okay, so now if we're going to start looking at the derivative of inverse sine, we're going to need to actually really understand what it means. So more than just being able to manipulate that expression we saw above. So to start with, let's just recall the most important fundamental thing here. And for the purposes here, we're going to use arcsine for our first derivation, because arcsine is the, kind of the most important one. Sine's the first trig function you get anyway. That's why they start SOHCAHTOA with s, because of the sine. So from here, what does that mean? Well, arcsine is just code word, basically, first of all, it's just another way of saying inverse sine. I like arcsine better because it's cooler, it looks different, it has more letters, and that little negative one is really annoying and confusing when you think about it, because it's not really an exponent. But again, they mean the same thing. So y equals arcsine, or y equals inverse sine, is of x, only is true if x equals sine of y. So think about that for a second. Basically, this if and only if thing is really just another way of saying these two expressions are completely equivalent. Like they're exactly the same thing. If y equals arcsine of x, then x equals sine of y. It's a lot like saying y equals ln of x if e to the y equals x. Like those same kind of things. Like same idea. It's an inverse relationship. Well, the reason we want to look at it this way is if we want to find the derivative of y equals arcsine of x, if we look at it in terms of x equals sine of y, we no longer have a new function. Like over here, arcsine, inverse sine, we don't know what the derivative of inverse sine is. We don't know that. It's just not one of our rules. We didn't cover that in chapter 2 last term. But over here, if we're looking at the derivative of sine, well, the derivative of sine is cosine. And of course there's a y in there, but having a function with a y in it isn't a problem for us because we know implicit differentiation. So in fact, the strategy we're going to use, and then I'm going to demonstrate for you in the first couple derivations and then in a couple examples that I'm going to work with, is using implicit differentiation and just stuff we know about trig. Basically, there's nothing else in here. Like you could teach well, I was going to say a monkey, but monkeys don't take honors pre-cal, so that's probably not a good example. You could train an honors pre-cal student to take this derivative. They just wouldn't know what they were doing. So again, all we're going to use is implicit well, okay, never mind, you can't because of the implicit differentiation. So just scratch that. But again, we're going to just use implicit differentiation, get the job done. So to start with, what are we going to do? Let's just write out what it is, what the problem is that we're looking for. So here, for our first real work here, now we don't need to call it an example. We just want to find y prime for the function arcsine of x. So what is the derivative of arcsine of x, otherwise known as the inverse sine of x? So go about doing this. What I'm going to do is I'm just going to demonstrate all the pieces. So we're going to derive it and find a formula for this expression. So to start with, y equals arcsine. As we said, we don't know the derivative of arcsine. Like that's just not a function that's in our repertoire just yet. So what I'm going to do is I'm going to rewrite this using the implicit form of it. That means that this is only true if x equals sine of y. So again, all I did, rewrite it. Now that I've rewritten it, I'm going to go ahead and take the derivative on both sides with respect to x, because of course when we want y prime, we're really looking for dy dx. Well, that's really easy over here. The derivative of x is just 1. On this side, the derivative of sine of y is just cosine of y, but of course because y is in there, like this is all defined implicitly, we need to use the chain rule, so it's cosine of y times y prime. And hey, look at that, we can see it right there. Like y prime is just sitting right there looking at us. Like we can see it. We wanted to find y prime. Well, there it is. It's waiting for us. The problem is we've got this y expression over here, like the cosine of y. Well, some of you might argue, well, let's just solve for it. So you would go, okay, let's divide both sides by cosine of y. Because of course that's what we do when we're solving these things. We end up getting, if I rewrite it in a little bit more normal order, we get y prime equals 1 over the cosine of y. And yeah, hey, we found the derivative. But of course, we want to find the derivative of y equals arcsine of x. Like, no, we don't want to have a y in it. Like, that's not useful. So what we can do instead is we can actually go back and draw out a triangle to represent our situation. And that triangle step is going to actually come in right there on that first place when we took the derivative, when we rewrote it, even before we took the derivative. So where is it? I'm looking right here. Basically, this says x equals the sine of y. So it says x equals sine of y. Well, that's the same thing as saying x over 1 equals the sine of y. Do you disagree? Well, you can't, and even if you did, I can't hear you because I'm talking into a microphone in my room, my study. So from here, what I'm going to do is I'm going to draw the triangle that has the sine of y equals x. So let's draw that triangle. Oh, that's a horrible triangle. No, it wasn't really. I was just being picky. So there's a triangle. This is the sine of y. So that means y is like our angle. The sine of y is opposite over hypotenuse. And so there we go. We found those two sides. Or we've labeled it all together. Now the sine of y equals x over 1. Well, of course, that's not a complete triangle. And what we want to know is we want to know what is the cosine of y. Because the cosine of y will allow us to get an expression for the derivative of arcsine all in terms of x. Well, that's why Pythagoras, or whoever Pythagoras stole it from, invented the Pythagorean Theorem, or came up with that. Up here we can find that missing side just by setting up the identity. So leg squared plus leg squared equals hypotenuse squared. Solving this around a little bit, I can trust that you'll follow my algebra. I'm going to get that the question mark, that missing side, is equal to the square root of 1 minus x squared. Why no plus or minus, you say? I've lost many a points from missing a plus or a minus. Why do you not need them now? Well, of course, because the side of a triangle is not going to be negative. So think about it. Yeah, got it. So from here, we've got our third side. The third side is 1 minus x squared, or the square root of 1 minus x squared. So now over here, we want to write out what is 1 over the cosine of y. Well, first of all, 1 over the cosine of y is just secant of y. Just another way of looking at it. So this way we've got the secant of y. Well, what is the secant of y from this triangle over here? Well, that's going to be 1 over the cosine. It's going to be the cosines flipped. So instead of being adjacent over hypotenuse, it's going to be hypotenuse over adjacent. And as it turns out, as weird as it is, we've just found the derivative of arcsine. In fact, I'm going to write it out right here. The arcsine of x, or the inverse sine of x, has the derivative 1 over the square root of 1 minus x squared. Like that is, well, you might disagree, but again, I can't hear you. The derivative, bad box, worst box. The derivative of arcsine is actually an algebraic function. 1 over the square root of 1 minus x squared. Go figure. I mean, who would have thought that was true? Well, I did, but it was because I knew it already. So, there we go. We've now derived an expression. We've got the arcsine of x is equal to that. So, hey, good for us. There's one. Let's go ahead and derive two more. Okay, here we go again. We're going to, again, derive another expression. And, of course, again, why are we deriving them? Basically, it illustrates the method really nicely, and this is what I would have done if we'd been able to teach this in class, if we had those 12 extra days that we don't have this term. So, again, what are we going to do? We're basically going to get this in a different form, and then use implicit differentiation and trigonometry to actually figure out what the derivative is for this function. So, in this case, what do I got? Well, if y equals the arc secant of x, that means that secant of y is equal to x. So right off the bat here, the last time I started going about the the differentiating and all that stuff. But in reality, at this point, as soon as we see that secant of y equals x, we can actually go ahead and think about what that actually looks like on a triangle. So they all are kind of similar to each other, but there's some differences depending on which one we have. So this says the secant of y, so the angle y, has secant, which is hypotenuse over adjacent, x over 1. It's not hard to figure out from there then, doing the Pythagorean Theorem, that the missing side on this triangle is x squared minus 1. So again, look at it for a second, think about it. 1 squared plus that thing squared gives you x squared. So now that we've got that the secant of y equals x, and we've got the triangle that has all the pieces we might actually need, we can go ahead and differentiate it. So we do have to remember some of the more exotic of the trig derivatives. In fact, this isn't too bad. So the secant of y. Well, the derivative of secant is secant tangent. So that means the secant of y's derivative is secant y tangent y all times y prime, because it's implicit, it's, you know, chain rule, all that stuff. Whereas on this side, the derivative of x is just 1. So nothing fun with x over there. So now from here, if I divide both sides by secant tangent, I'm going to get that y prime equals 1 over secant y tangent y. And again, we end up with it in the same place we did last time. Last time it was y prime equals 1 over cosine y. Here it's 1 over secant y tan y. So just like last time, I'm going to go ahead and rewrite this guy. I'm going to rewrite it as cosine of y, because 1 over secant is cosine, times cotangent y, because 1 over tangent is cotangent. And then I'm going to go up to my triangle and pull out all that information. I'm going to get 1 for each guy. So looking at this, first the cosine of y. Cosine of y is 1 over x. Cotangent of y. Instead of being opposite over adjacent, that's going to be adjacent over opposite. Adjacent over opposite. So 1 over the square root of x squared minus 1. So from here, for my final answer, what is the derivative of y prime? Well, we're actually seeing it right here. So for arc secant of x, the derivative is equal to 1 over x square root of x squared minus 1. Now, before I box that, I do have to make one little caveat, one little adjustment here, and that comes from the fact that that x down there represents a part of the triangle which has some restrictions on it automatically. So think about it this way. Up here on this hypotenuse, this is equal to the sum of two squares, one leg squared plus another leg squared. That value has to be positive. So again, if you don't remember why, look at the Pythagorean Theorem, it tells you that side has to be positive. The problem is x by itself is just waiting to have a variable plugged into it, a number plugged into it. Could be a positive number, could be a negative number. Well, to restrict it, to make sure that our answer still has x as a positive number to represent the hypotenuse of a triangle, we do have to add one thing to this. The derivative of arc secant of x is actually equal to 1 over the absolute value of x times the square root of x squared minus 1. So now we've got our final answer. And again, you'll see that in textbooks. Sometimes it matters a lot, sometimes it doesn't affect it a whole lot. Sometimes you just can't draw a box no matter how much you want to. But there it is. Now we've derived an expression for the arc secant of x. So its derivative, or an expression for its derivative. Its derivative is that. Another thing involving an algebraic function. Kind of cool. Let's go ahead and do one more. Let's do tangent, and then let's kind of regroup and do some of the harder problems, or some more involved problems, and show you how beautiful this method we're using actually is. Alrighty, final one. So what is the derivative of arctangent of x? At this point, if we're following the leads of the last couple, we should probably be expecting something with square roots, x squareds in it, and 1s, because, so far, so far. And of course you might be wondering why I'm going to stop at arctangent. You'll see in a second. So, arctangent of x, or the inverse tangent. So start out the same way. If y equals the arctangent of x, then tangent of y equals x. So again, we're just rewriting it in traditional form. From there, that would be describing a triangle in which the angle y has tangent opposite over adjacent. From here, again, not hard to follow. If those two are the sides, the other one will just be the square root of 1 plus x squared. So there's our triangle. We already got it. It goes really fast. You'll get used to this really quickly as you go through. So from here, we want to calculate the derivative of this thing, because we want y prime. We want to figure out what is that rate of change expression for arctangent. So from here, derivative of tangent. This is one of the fun ones. It is secant squared of y times, of course, y prime. And the derivative of x is, no, it hasn't changed yet. It's still 1. So from here, we've got secant squared of y times y prime equals 1. Well, if I go ahead and divide both sides by secant squared, I'm going to get that y prime equals 1 over secant squared, which is just a fancy way of saying y prime is cosine of y squared. Because, of course, secant squared, 1 over secant is cosine, so this just becomes cosine of y squared. So from here, all we have to do is go back up to our little picture. Look at our triangle and actually see what is cosine. Well, is going to be squared whatever it is, and the cosine is adjacent over hypotenuse. It's going to be 1 over the square root of 1 plus x squared. So when we square that, we get that it's 1 squared is 1, square root of 1 plus x squared is 1 plus x squared. And wow, that is an awesomely, ridiculously simple looking derivative. So in fact, our final, well, you'll see why it's our final one, the derivative of arctangent of x is actually equal to the beautiful expression 1 over 1 plus x squared. So again, this method has given us some pretty nice mileage. We've come up with 3 derivative rules we have never seen before in our lives, unless you cheated and looked ahead in the book. I hope you didn't look ahead in the book. So there it is. Derivative of arctangent, 1 over 1 plus x squared. So let's inventory these guys for a second. Well, at this point we've already kind of got it there, so let's inventory them for a second. Okay, so at this point, if I inventoried things just a little bit, this is what we know right now. We know that the derivative of inverse sine is 1 over the square root of 1 minus x squared. We know the derivative of arc secant, or inverse secant, is 1 over the absolute value of x times the square root of x squared minus 1, and the derivative of arctangent is 1 over 1 plus x squared. The question you might be asking is, well, you missed something. What about arc cosine? What about arc cosecant? And what about arc cotangent? Well, I don't want to spend a lot of time going through where those derivative rules come from. So instead, I'm just going to play a little thought experiment here. So let's imagine instead of doing arc sine, we'd start with arc cosine. Well, really, if we think about it, what would have changed would have been we would have had x equals the cosine of y. The derivative of cosine of y is negative sine of y. So all these same ingredients would be involved. The only thing that would be different is we'd have that negative sign floating around. On secant, if we'd done cosecant instead, the derivative of cosecant of y would just be negative cosecant y cotangent y times y prime. So again, we'd have a negative floating around. Everything else would be kind of in the same spot. We'd be looking at the same ingredients over and over again. We'd just have some relationships switched around. And finally, for tangent, if we'd done cotangent, the derivative of cotangent of y is, well, you guessed it, negative cosecant squared of y. So we just have that negative sign floating around. And in fact, the reason we've held off on grabbing those rules, and by even going through them, and we're not going to even go through them, comes from the fact that their derivatives come the same way. If we did them, we'd have almost perfectly parallel derivative rules. In particular, those derivative rules would be these ones. The same exact rules with a minus sign thrown in. So that's it. It's the only difference. So in fact, all the inverse trig derivative rules you could ever want, well, there are actually only 6 of them, so all you could ever want is those 6. Those inverse trig derivative rules are right here, given by these 6 expressions. Now, with that said, again, if you're one of those people that loves to memorize things and you don't actually want to learn a process and you don't care if you make mistakes all the time and miss points and, screw up on questions that are easy, you might just say, hey, this lesson's over. You just go memorize these rules and then you apply them and you use the chain rule, the product rule, the quotient rule. Use all those rules and you just deal with it and you enjoy it. But if you're one of those people that likes to get things right and is comfortable, doing 8 problems that are, asking you to apply a simple method, and you're good at things like implicit differentiation and trig, well, there's a way that we can use these, or we can basically avoid ever having to memorize these rules. We can just basically solve every problem by doing it the same way we have here, by deriving basically what the derivative rule is in any situation. So it's going to seem a little weird, and it'll probably take a little bit of work, but it's not going to take an unreasonable amount of work every single time. We just have to actually go through and figure out what the derivative is. So what I'm going to do is I'm going to move forward from these derivative rules, and I'm going to simplify or use this method in a problem that we haven't done yet. And I'll list the steps in the plan as I go through. And then, of course, I'll try to do an example that's a little bit harder with each one. So what I'm going to do, what I'm going to start with, is I am going to write out a problem for us to differentiate. And I'm making it up as I go because I have so much confidence in this plan of mine. So what we want to do is we want to again find the derivative. I'll be a little more interesting, and I will write out the instructions as differentiate. And we're going to differentiate, forget it, y. Y equals 5 arc sine x squared over 3. So we're going to find the derivative for this expression. So if this were the olden, well, this wouldn't be the olden days. If you were one of those memorized people, you'd just have to stare at it and kind of go, oh, the arc square root, there was an x squared in there. God, memory work. And of course, you'd just sit there and you'd have to memorize something that's kind of confusing in the first place. I mean, look at all those square roots and squares and all that stuff. If you're me, and you're following my method that I've used all the time without memorizing anything, you could actually begin this problem pretty simply. And that is by rewriting it so that it looks like sine of stuff and then equals to a value or an expression. So I'm going to do that first. So I want to be able to rewrite it so it looks like x equals sine of y. The problem here, of course, is that there's more going on. We've got a bunch of weird stuff on the inside. We've got this 5 out here. So the first thing I need to do is I need to divide both sides by 5. Like if this is true, it means that y over 5, it's a terrible 5, y over 5 is equal to the arc sine of x squared over 3. And that means then, if we go one step further, that the sine of y over 5 is equal to x squared over 3. So think about it for a second while I fix that 5, because someone's going to complain about it even though I can't hear you. This expression means exactly the same thing as what's written up there. The reason we did that is because it's going to be a lot simpler to play with and differentiate. So now from here, what I'm going to do is write out this in steps. So my first step that I just did in evaluating this derivative, or finding this derivative, is I rewrote it into a form I could work with a little bit nicer. So rewrite your way out of the inverse trig. So I did that because now it says sine of something equals an expression. So that was step 1. Step 2 is going to be to actually differentiate implicitly. So now we use implicit differentiation because it's a lot easier to do that. So looking at this guy, I need to take the derivative of both sides of this guy. So let's start on the left side. The derivative of sine of stuff. Well, the derivative of sine of stuff is cosine of stuff. And then, of course, we have to multiply times the derivative of the stuff. So the derivative of y over 5, that's the same thing as 1/5 y, which means the derivative of that is going to be equal to 1/5 y prime. So again, if that doesn't make sense, think about it a little bit, rewrite it maybe, you'll see it. On the right side, all together now, what does this equal? 2x over 3. Caught myself there, I knew you couldn't answer because you're not here. So there's our expression. Y prime is what we want. We've just got to figure out what it is. So all I've done is taken the derivative implicitly. Now step 3 is going to be to draw the triangle. So of course when I draw it, I'm also going to need to complete it using Pythagorean Theorem. So we draw and complete the right triangle that's represented by our original expression. So let's look at it. Let's see. Y over 5 equals arc sine of x squared over 3. So I'm going to use this guy, not the exact original one, because that 5 in front otherwise would cause us problems. So there are a lot of ways we could do this problem. I'm doing it the way I think is easiest. So this says over here that the sine of y over 5, so the sine of the angle y over 5, is equal to opposite over hypotenuse. So again, take a look at it for a second, think about it. You can see that it's true. Okay, so from here we need the missing side. Again, I've gotten a lot better at this, but use Pythagorean Theorem. So this side square, or the leg squared plus the missing leg squared, has to equal 3 squared. That means this whole thing, this missing side, is going to be 9 minus x squared squared, which is x to the 4th. So the missing side was the square root of 9 minus x to the 4th. We've got a complete derivative, or a complete derivative, not yet. We've got a complete triangle staring at us now. So, great. Our next step is now we are going to solve for y prime. So because we're getting close to that point where we can actually substitute some of this stuff. So solve for y prime. So now we're bouncing back to the actual derivative stuff right here. So if I want to solve for y prime, I need to, let's see, I'm going to multiply both sides by 5 to get rid of that 1/5. So I'm going to get 10x divided by, and then if I divide both sides by cosine of y over 5, get this equals y prime. It's a little weird looking, but it's okay. Like, we're in good shape. So from here, what do we have to do? Well, now, finally, we need to substitute from the triangle. So let's get a good color here. How about blue? So how did I describe this? I want to make sure I do it correctly. Use triangle or substitute from triangle. So now we look at that triangle we created to figure out what is the value of the trig thing that's left in our expression. So what is the value in this case of cosine of y over 5? Or if we want to rewrite it, which we very well could, we could have 10x over 3 times the secant of y over 5. So all the same. Well, cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. That means that this whole thing is going to be 10x over 3 times hypotenuse over adjacent. So what happens? Well, we got to simplify then. So I guess there's technically as a last step in here. Step 6 would be to simplify, although I think that goes without saying, or writing, or whatever it is I'm doing here. If we simplify, the 3's are going to cancel. We're going to be left with the derivative as 10x divided by the square root of 9 minus x to the 4th. And there is the derivative of that expression. We found our derivative. So again, our method, pretty darn effective if we look at it right. So again, how do we find it? We rewrote it in a form we could work with. In this case, we had that weird divided by y thing, 5 thing, but it worked out just fine. So trig of something equals something. We drew the triangle so that we can, and completed it so that we'd eventually have the tools we need. Then we solved for y prime after we took that implicit different derivative. We solved for y prime, and then we substituted using the triangle that we'd had in the first place. And we get our value of our derivative. Notice if we hadn't done it that way, if we tried to do it with the chain rule, we would have had to plug in x squared plus 3 multiplied by its derivative at the end. We would have had some complicated thing on the inside. Like, there would have been all sorts of messy things we would have had to deal with. This is a lot better. And I feel completely confident saying right now that this is a lot better. And you will have success if you follow this method. If not, I will happily, gleefully take away lots of points from you when you make mistakes. So, from here we've done one example. Let's do one more before we call it a day, and leave you to master it, the rest of it on your own. Alrighty, so our final example here. And what we're going to do is we're going to do one that's not hard on its own. It's just the fact that we're going to have to involve some other rules in the problem. So in this case, what we have is a function that's defined not just in terms of an inverse trig function, but also something else. So y equals x cubed times the arc cotangent of x over 4. Now, of course, this function, you may not have seen it before, but it actually comes up all the time in the very practical application of UFO maintenance. When an alien race actually has to build their UFO, the turbulence engine that they use to counteract the repulsive forces of gravitation outside this Earth's atmosphere, like when they're about to enter the stratosphere and start spinning the neon lights, the functions in the turbulence engine actually use an expression along this way to calculate out the anti-gravitational Higgs boson. So, of course, you've got to know this in real life when you're... yeah, okay, that died. Sorry. I tried. So for now, all we're going to do is we're going to differentiate this. Why? Because the calculus textbook asks us to. So from here, we want to differentiate it. Well, to start with, before I do anything else, before I start rewriting, I need to adhere to the product rule and make sure I know where it is that I need to do all this stuff to find the derivative of the arc trig part. So using the product rule, y prime is going to be equal to the derivative of the first function times the second function, which happens to be arc cotangent of x over 4. And then, of course, plus the derivative of the second function times the first one. Well, now, we don't need a 6-step plan to deal with the derivative of x cubed. That's just 3x squared. We can just rewrite whatever the other one is. But over here, aside from the x cubed, dealing with the derivative of arc cotangent of x over 4 takes a little bit more work. So what I'm going to do is I'm going to basically create this other guy. I'm going to think of this as my y, and then I'm going to do my work to figure out what this guy's derivative actually is. So in this case, I'm thinking of this guy now as my y. So it's a little weird, but you just got to bear with me. It's the easiest way I can think of doing it. Basically, I shorten the problem. I deal with the problem itself and as a whole with the product rule, and now I'm going to shorten the problem just to an inverse derivative, or an inverse trig derivative. So now we're off to the side. We want to figure out what is the derivative of arc cotangent of x over 4. So I do the normal process. Now I'm going to rewrite this guy. So what is the derivative of this guy? Well, this is the same thing as saying cotangent of y equals x over 4. So now we need to take the derivative of that guy. So the derivative of this guy, following the old method, cotangent of y, its derivative is equal to negative cosecant squared of y, and of course times y prime. Don't forget that, it would be a shame to lose it. And then of course the derivative of x over 4 is just 1/4. So what we're going to do is we're going to now draw our little triangle. So our triangle, in this case, is going to have just the angle y, and its cotangent, adjacent over opposite, is going to be adjacent over opposite. So the tangent is 4 over x, it is. There we go. Missing side shouldn't be hard for you to jump to. The missing side is going to be x squared plus 4 squared, otherwise known as 16. We don't call it 4 squared because then people would think it was that game played on playgrounds at recess all across country. Now that we've got our triangle ready to go, we can go ahead and do the solving work. So y prime for this guy, for this star, for this little expression that's eventually going to go here, the y prime for this guy is going to be negative 1/4. Well, it'd be technically negative 1 over 4 cosecant squared of y, but of course 1 over cosecant squared of y is the same thing as sine squared of y. So I'm going to look at it as negative 1/4 sine of y squared. The reason for that is now I can look right at my triangle, substitute directly from it, and figure out what this expression actually looks like. So in this case, sine of y, opposite over hypotenuse, is going to be negative 1/4. We're going to have squared opposite over hypotenuse, which means that our y prime here, or really the derivative that's going to go in here for star, is going to be, let's see, so negative 16 over 4 is just going to be negative 4, divided by, since that thing's squared, x squared plus 16. So this guy is star. I throw it in right there. Well, technically I'm not. I'm going to drag it over to this side. Because now we're ready to move on and finish this problem. So that derivative that we were looking for, just kidding, we'll leave that there. That derivative is negative 4 divided by x squared plus 16. So to finish off this problem and simplify to our final answer, let's see, it's not going to be pretty no matter what I do. I see 3x squared, arc cotangent of x over 4. Again, everything we do from here is just cosmetic, so don't stress too much about this if it seems like a lot of work for not a whole lot of stuff. Then we'll have divided by x squared plus 16. So all I did was multiply those two together, thinking this is over 1. I've got this expression. Now from here, is this the wrong answer? Is this the final answer? It depends on what you want or how satisfied you are with that messy thing. I'm going to do a couple things. First thing I'm going to do is I'm going to find a common denominator. So I don't have to, I just like to do it. Otherwise that could be a perfectly acceptable, although very ugly, final answer. I can multiply up and down on this first term by x squared plus 16. And then I'm going to factor out a GCF of x squared and x squared plus over x squared plus 16. So again, it's a little bit of algebraic movement, but bear with me. I'm going to end up with, I hope I'm doing this correctly, x squared over x squared plus 16 times, looks like 3 x squared plus 16 from the top, arc cotangent of x over 4 minus 4x, and nope, that's not there anymore, minus 4x. And so this guy, this little mess down here, is our derivative. Now, of course, I don't trust myself at this moment, but I don't have a T89 sitting around anywhere, so I'm going to check it on my phone really fast using symbolic calc. I would show it to you. I'm showing it to you right now like a la Vanna White, but you can't see it. So I'm just narrating through the process. I'm going to ask it to diff, that's slang for differentiate, for me. Yeah, me and symbolic calc are tight like that. Differentiate, let's see, this guy. Wow, that's messy. Okay, so it multiplied it all out for me. So it gave me x squared over x squared plus 16 times the quantity 3 x squared plus 16 arc cotangent of x over 4 minus 4x. Booyah! Think we got it. Looks like we found our derivative, didn't we? Again, process very messy. This answer right here in pink would have been just fine if you're satisfied with that kind of stuff. But again, the idea is, in order to take this very complicated derivative that's, well, we stopped that, never mind. In order to take this very complicated derivative, we had to use what we just learned, this method with inverse trig. But more importantly, we had to use the product rule first, and then use our little method kind of off to the side to kind of work it through. So it's kind of like that inverse trig part was just its own little game. Not difficult in any sense, just something we had to do. So, to kind of recap what we've done here today, to deal with inverse trig derivatives, we start by reviewing this idea of inverse trig back from pre-calculus. Worked through it, did an example there. Then we started actually deriving these derivatives just by rewriting things from inverse trig to regular trig and using implicit differentiation to make up the gap, or to make up that deficit that we had. Did it a couple times, came up with 3 formulas for arc secant, which had the little absolute values in there, and then the beauty that is arctangent's derivative. And then basically we talked a little bit about why it is we don't need those other 3. They're just the same things with a minus sign in them. Nothing big. From there we started using this method, and I used one big super example basically to illustrate it in all its glory, and to illustrate how we really don't need to memorize these things. I mean, we could basically just scribble them all out like so. We don't really need them in any way. I'm not going to do that because it took me a while to type them up. But the idea is we don't really need them. We can just use this method of rewriting and implicitly differentiating. Then we did one with the product rule just because, you know, in case anyone's driving a UFO over spring break, I want to make sure you're covered. So from there, you've seen it all here. Your homework should be even more basic than anything like this. And again, hopefully, I hope that you do enjoy your spring break. I hope that this calculus has been a momentary distraction and it doesn't bother you too much that you're doing it. But again, my goal is to make you pass the AP test, or to allow you to pass the AP test if you so choose, and give you everything that I can. And I don't have as many days as I did last term, so this is one way we can do that. So anyway, for Mr. Steele, well, I don't have anyone else to say that for. For Captain Kirk, Mr. Spock, and Mr. Steele, this is Mr. Steele. No, that's stupid, I don't have to say that. So enjoy the rest of your break. Hope these videos were at least mildly entertaining. Good luck with your UFO maintenance, you know the function now. And again, enjoy the rest of your spring break. Thanks for watching. Bye.